Okay, so you heard about fluid mud problems in rivers and estuaries, but also you can have fluid mud problems in lakes and wetlands and um, salt marshes and tidal flats. So if you look at the eastern seaboard of the US, those are the more important problems than fluid mud in the channel. That's number one. Number two is that material that forms fluid mud is very organic. So it may have very little clay. The organic flocks, they behave like inorganic flocks, and they don't compress very much. So if you drop them in water, they'll form a layer, and that'll have a certain density. And then if that layer happens to be on a slope, then it'll roll down. So that's the kind of problems we have. But the real problem is contamination. Now this, for example, is I'm going to talk about Florida, where there are quite a few lakes, as you know. And this lake, Lake Apopka, which is near Orlando, is the most polluted lake in Florida. And it has all of this pollution started over 100 years ago. So when you say pre-Columbian in Florida, that's not 400 years, that's just 100 years ago. And so if you compare the amount of organic material in the streams of Florida from pre-Columbian times to present time, there is a 1,000-fold increase in the concentration of organic matter, which then ends up in these lakes. And then on top of that, a lot of these lakes were surrounded by farms where there was sugarcane and other orange groves and pineapple. So all that phosphate in the early part of the 20th century and up to mid 20th century went into the lakes. And it formed a thick layer, in some cases as many as 2 meters, 3 meters thick. So a lot of these lakes, which are naturally deeper, are actually very shallow. They only have 2-3 meter depth, because below that is 2-3 meters of what's called organic muck. And that always remains very fluid. It cannot, as I said, it doesn't consolidate. So it remains fluid and it rolls down. So if you have waves and flow goes around in the lake, then it stirs up the material. So let's see, what do they do right now in Florida with that? So I have to go to the second slide. Let's see here. So what did you do, Susana? Huh? This slide shouldn't be here. Anyway, we can use some imagination. So this is Lake Apopka. You can just see part of it. And this is a canal that runs from between this lake and the next lake. And this canal is used to control the water level in the lake. So what they do, and this is the standard practice of how you try to improve the water quality in lakes in Florida. So you create these wetlands. They are it's a kind of a grass that grows here, pickleweed and other stuff, and then you pump water from here, and then it goes down here and goes into the canal and then back into the main lake. So these areas are used to pick up all the organic matter, and so the organic matter settles down here, and you keep doing that all the time. So clearer water comes back here. And for example, since 2003, this system removes about 4,500 tons of suspended solids and 2.3 tons of phosphate. And then you have to, the phosphate and all that stuff that deposits here, you have to stop the flow and then recharge the whole system. So that's how lakes in Florida are controlled in terms of their water quality. Now, what they have also done is the government has bought all the land around the lake. So there are no more farms. For the past 50 years, there have been no more farms, no phosphate introduction, and no pesticides also, because there are also pesticides in this lake. The problem is that there is so much sediment here that it's impossible. It could take hundreds of years if you run this system to actually clean the lake, because there is already a tremendous inventory of phosphate and in the, as I told you, several feet of muck that resides in the lake. So what I'm going to do is just give you a brief idea of what it means for this kind of mud to roll down a slope. Because if you can make it roll down, then you can collect it at the downstream end and pump it out. And but this is mostly notional, because the cost of doing that for this whole lake is astronomical. So they haven't done anything. So you can see where this lake is here. This is Orlando, and this is the largest lake. This is Lake Okeechobee. This is Miami area, and that's the Cape Kennedy Center. So you get some idea where the Orlando, Cape Kennedy, and these lakes are internally connected to control the water level, but it doesn't help the water quality there. So you can see here, and the wind blows, the wind rose is, it blows from all directions. So at any instant of time, you get a very complex circulation of water. And but what that does is that if you have, because the lake is laden with very soft organic matter, it has become fairly flat. So there are not very steep slopes. Fortunately, you don't need a steep slope to make the fluid mud roll down. So let's look at the essential issue of what is involved in causing the mud to roll down. And you heard about that from earlier presentations, that you have to look at the relationship between stress, that is due to wind and waves, and the rate of strain that is produced in the sediment. And let's see. So here is a notional vertical section of the lake sediment. You have fairly clear water here, small flocks and particles. And these are all mainly organic. You have to remember that. Then there is a layer here which has more flocks in it. And then you have a layer of fluid mud. And the difference between this layer and that layer is that the rate at which this settles is very, very low, because there is too much sediment here. The flock layer, these are the two layers that really go up and down during wind events. And only rarely during wind events this thing is disturbed substantially. It almost never goes down to this level, which is what is called the bed and a bed. And so there is a transition here from very dilute suspension to what would be called a kind of a non-Newtonian suspension, to fluid mud, which is even more non-Newtonian. It has a fluid, it has yield strength, although there is some yield strength here also. And then this is a solid, and then below that is a solid. So it's this layer here. If you do calculations by mass, how much sediment moves horizontally, you see that most of the sediment is contained in this layer. So it's this sediment that you have to take out. You can, right now, as I showed you, the system works to take out this stuff here, and it really doesn't do very much for this. So the question is, what is the rate at which this sediment flows? I mean, if you make a hole somewhere, and you want to know how long it will take for the hole to fill up, or maybe to look at it other way, how much sediment will accumulate in that hole in 1 year, so I can go with my pump and suck it out, then you have to do simple calculations, and you have to look at this stress versus strain relationships. So this is the kind of stuff that these are chloroplasts, purely organic, and then you have here you have this system where there are some solid particles. The rest of it is polymers, so exopolymers. So this is the kind of stuff that floats around in this, and in this place here, all of this stuff is settled, and in this here, in this region, this is mobile. So let's look at a very simple model of what it means for fluid mud to float, to move down. And so if you look at this is a two-layered system. Here is water, and here is fluid mud, and the fluid mud has a constant density. But it's very, it's because it's constant density, the shear stress here is linearly increases with depth, and you have this profile here. What's happening here is that this fluid mud has some shear strength. So in here you can see that this whole layer, the shear stress is too small here in this layer from H0 to H to cause this layer to shear. So it all moves down together. This layer at the top moves down together, but below that you have higher shear stress. So if you look at the shear stress, it increases, and at this depth here, it's greater than, below this depth, it's greater than tau sub y naught. So if tau sub y naught is the shear strength of this mud, then this layer shears. Actually, you can see the velocity profile is decreasing to 0, whereas here it's what is called plug flow. So it moves down as a single plug. So if we want to know how to calculate how much sediment is moving down this fluid mud, we have to know what this velocity profile is. So if we know that velocity profile, we have basically solved the problem. And the other part is what I mentioned is that you have to know the relationship between the stress, this is due to fluid, and the strain rate, which is in the fluid mud or in the mud. And the most simple model is where you have a straight line here. So this is the yield strength, and then it increases. So if it's a straight line, it means that the viscosity of this material doesn't vary with this gamma dot. This doesn't vary with the shear rate. It stays constant, and so the viscosity eta is constant. But below this, but what actually happens is that the curve looks like this. And so this is the yield strength, and then initially the shear strength rises very, the viscosity decreases very fast because the viscosity of this suspension is this slope here. So high slope here, low slope here, and then it becomes constant at very high rates of shear. And it changes the structure of the fluid mud or the mud, and below this tau y naught, as we mentioned, it doesn't move. Above tau y naught, it becomes a fluid, and then eventually it becomes a Newtonian fluid. So the structure of the system changes from something like this to something more organized here. So the important point here is that as you increase the stress and as you increase the shear rate, the structure of the material that is experiencing this stress changes. So it's a very strong structure here, and it starts breaking down, and then here it becomes a pure fluid. So there are many models that describe this. And so one important point is that in the simplest model, we would use this straight line. However, if you look at lakes in Florida, most of the action takes place when the shear strain rate is in this region here. So a slight change in the shear strain rate changes the viscosity, and that changes the rate at which the fluid mud accumulates in the hole. So we should be able to model this somehow and not have to use this very simple model which assumes a very different rheology than this model. So a lot of people have actually worked on that for decades, and especially in chemical engineering, to come up with an equation for this line here. And but the one I find very kind of interesting is one where an explanation is given. The equation is derived, and an explanation is given, which tells you that to get this particular function, you have to allow for the structure to change from this at this end to that at that end. So that model is also quite well known, and so I'm not presenting anything new, but let's see. So it's that model is by these two people. I think they were chemical engineers, and then Moore, and these two sets of investigators derived an equation for this blue curve here, which with the specific interest in making sure that this thing is modeled correctly, and that it's not a straight line, but it increases like that. So what happens is that any locus on this blue line, as it moves from here to here, the strength of the material that is being affected drops from this point at this point to at this point. That one goes to 0. So the shear strength goes from tau y naught to 0. And so they introduce this so-called structural parameter, which is 1 maximum here and 0 when it becomes a fluid. So solid starts as a solid and it becomes a pure fluid. Now we won't go into the detail, but it turns out that this structural parameter is a dynamic quantity. So to calculate it, you have to look at this equation, which equates the rate of change of gamma, the lambda, to a growth function and a breakup function. And if you have, and that could be anywhere, but if you are on this curve, then you have what is called an equilibrium condition, and for that you set this equal to 0, and you get the value of the equilibrium value of lambda sub e, and you can see that lambda sub e is a function of gamma dot. So as gamma dot increases, lambda sub e decreases to some final value. And then finally, if you work out the equations, which very well described in this article, but you have to read this article quite carefully, because to make sure to understand what has been done. But what has been done is that you get an equation for tau, the shear stress, and you get an equation for viscosity. And then you can use a simple rheometer. This is a Brookfield viscometer to measure to measure the shear stress against shear strain. And then the circles are data points, and this is The lines are based on that equation. And so you can see that here the density of the material is 1014, and recall that earlier today you saw much higher densities like 1200 and stuff like that. But organic sediment starts becoming fluid mud because it has this high elasticity. It doesn't consolidate, and it becomes fluid mud at very, very low concentrations. And here it's 1011. So you can see that a small change in the density from here to here has a substantial effect on the viscosity. So it's important to really use this kind of a device to understand the exact way in which the fluid mud that you are working on, how its properties control the viscosity. So this is my last slide, and this equation has been solved by Van Kessel and Case Kranenberg. It's a really nice paper where they have provided an equation for this function here. So once you have the velocity, once you know the velocity, you multiply that by the density rho, you get the load. So if you now what I did here is in this model you cannot use the Worrell-Tuliani equation. So I just use the regular equation for the straight line equation that I showed you. But be that as it may, you come up with the unit mass load, that is the amount of mass that flows down per unit width of this perpendicular to the board here. And so you can calculate how much is going to move. So if you have a trap here, you know how big the trap should be if you know how thick the fluid mud is and what its viscosity is, to determine how much trap size you need to catch the sediment. Let's say that if you want to go and pump it every year or something like that to for that purpose. So just an idea of, now this method here would actually take out the fluid mud. The present method that I showed you doesn't do that. But this is also very expensive. It's extremely expensive. The lake is 14 kilometers by 14 kilometers. And the cost of cleanup of the lake is $700 million. So the problem is that you can't just take it somewhere. You have to do something with this sediment. So nobody is going to do any of this stuff. No one.